All right, today we're going to talk about troubleshooting methods in our next lecture for Intro to Logic and Troubleshooting. So here's a brief outline-ish of the talk that we're going to have today. So we're going to look at troubleshooting techniques. And these are really tools in your engineering toolbox. I want everybody to think about it like that because it's really easy to categorize this in your brain and organize it so you can access this information if you think about it as such. Tools in your engineering toolbox. So we're going to break these techniques down into two separate kind of flavors. We have first the higher order methods, which look at systems and try to break big systems down into smaller systems or get information out of big systems, and component-wise methods. So this is when we actually identify which of the subsystems has the problem, and then we look at each of the components and basically identify which of the components is causing the failure. All right, so I want to be clear that everything we're going to talk about today is still within this 7-step method. In fact, it's really like kind of a mix between steps 2 through 6. So we gather information, we analyze information, we decide if the information is sufficient, we propose a solution, and then we test the solution, all in these methods that we're going to learn today. Um, Using these methods will make you much more efficient at troubleshooting, so I suggest you implement them, and you'll find that different methods are applicable for different stages of the troubleshooting. All right, so first let's look at higher order techniques. So first and foremost, we're going to look at taking a big system down to smaller, simpler subsystems. So this is called complex to simple in the book. So we did this before with this example, actually. We looked at this the same example where we have hot oil coming in. It goes through this heat exchanger here, and it basically provides heat to this cold fluid over here. The hot oil has a flow rate that's controlled by this valve and has this array. These are all the components that are involved with the controlling of this valve. And the cold liquid over here has a tank that has a level. And once the fill amount reaches a certain point, it turns this indicator, it turns this float switch or this transmitter on, and then we open the valve and let some fluid out of the bottom. So very similar to our feed water problem, and also we've looked at this before. But so if I get an error from this system, and I'm not told much information, I'm just told something's not right, or the cold side isn't heating up any. That doesn't give me a whole lot of information. That doesn't tell me which of these subsystems is actually the problem. So in order for me to take a second and actually start troubleshooting effectively, it's easiest for me to break this down into the two subsystems like we did previously. So I have the hot side on the left, the cold side on the right, and I turn those into black boxes basically. They have inputs, they have outputs, they have power supplies, they have some sort of references, maybe for reference temperature, reference pressure. And there's also external effects on the system, ambient temperature, ambient pressure, and then effects on other systems. So information coming from other systems in or out that informs this system to do something. So simplifying the overall system into subsystems will definitely help identify which of these subsystems is actually failing. Is it the flow control for the hot oil, or is it the fluid level control for the cold fluid? All right, the next method is circle the wagons method. So this is similar to the complex to simple, but almost in reverse a little bit. It's a little different. So basically, what you do is you take a system and you draw a circle around the entire system. And then you look at all the inputs and outputs that go into the system, every single thing you can think of. So here we have input signal, output signal, sure. But we also have power, grounding, interface with some operator. There's an interface boundary here, but there's also some electromagnetic interference that could be coming into the system. And then on this bottom example here, I have a subsystem, or I have a array of systems, and then there's all these different pieces of information that are coming in from the surroundings. So again, electromagnetic interference, but I also have people. I have some background noise. I have the ambient temperature. I have leakage, any sort of heat leakage, or even um, like current leakage, and then I have some grounding, some noise, and then I have signal, and so there's a lot of information that can go in or out of your systems. And in order to make it easier for you to start troubleshooting where the issue lies, sometimes it's easier for you to do the opposite and kind of take the system, draw a big circle around it, and make it, make it one big system rather than each of the components in the subsystem. Make it one big system so you can kind of identify what's coming in, what's coming out, what's going to impact my system. So this is the opposite, really, of the complex to simple. All right, so these are failure identification techniques, and really what these are component-wise or subsystem-wise troubleshooting techniques to identify the failure component. Okay, so the first and probably the simplest is the substitution method. So basically, you install a known component for a suspected faulty component. Is my pump not going to go? Come on, pump. You just take it off the shelf. So you probably have some inventory. Oh, the pump's supposed to go. Hold on, come on. There she goes. You're supposed to have some inventory, or you likely have some inventory at your shop or at the facility, and there's probably things such as pumps, valves, stuff like that on the shelf. You can test those to see if they work, and then if they do work, you just install them for the component that you thought was faulty. If that component was indeed faulty and you install a working component, the system should now work nominally. It should go back to normal operating conditions. One thing that you want to consider, this is this disclaimer down here, is that if there is a higher order failure, so if there is a failure that's occurring, in the DCS, which is again just controlling, this is talking to this liquid level control unit. This is a DCS, so distributed control system. If there's an error with that, or if there's an error with your power supply or something like that, that may cause the good component to fail as well. So if there was an initial surge or a transient event that occurred that blew out, you had so much current running through your component that it blew out the circuitry in there, it's going to do it to the new one. So you need to make sure that if you install a new one, you're positive that that's not what caused the issue, and or you implement some sort of safety net in the circuit just to make sure. All right, so the next method is called divide/remove and conquer. Basically, for loosely coupled systems, or for systems that aren't dependent on all the components in the system being there, we can just kind of unplug and see what happens. And that's exactly what this is. So this is particularly useful when troubleshooting a communication system. We basically just unplug it and see how the system responds. So as we disconnect it from our main system or our main communication system, what is the response of the rest of the system? And the inverse of this would just be to add components. So basically disconnect everything and add components back. So it's best practice to complete this in both ways, so we can really figure out which of these components is causing the issue and be dead sure before we move on to proposing a solution. All right, so the next method is called the fault insertion method. So this works by basically installing a fault simulation array. That's this component here. That's the fault insertion unit. So this component right here is designed to simulate faults. So there's 3 gates, and you'll notice if the top gate is closed, we're working at normal operation or nominal conditions. So this is under normal operating conditions. If the center gate is closed, we simulate a short to ground. And if the bottom gate is closed, we simulate a short to power. And this is done in order to simulate what the system does or how the system behaves when there is this fault or this fault present. And so this is done a lot actually in software development as well. So if there is an issue, basically you want to know why, or where the issue lies, and be able to communicate this. And sometimes you want to throw, say you have something, you built a code that calculates something, you want to throw errors into your code, and you want to implement, or I guess introduce, errors in the code to see how it handles, or introduce errors into the input and see how your code handles the errors as inputs. What is it? Does the code completely like crap out, or does it actually handle it and maybe inform the user, hey, this is the mistake you made. This is the type of input I need. Please rerun the function and basically include this type of information. All right, so the last one is called trapping. So this is what occurs when basically we set up a trap within the circuit to catch a transient error. And really, you can do this one of two ways. So the first way is some sort of mechanical trap. So a fuse, a breaker, some sort of mechanical latch. You'll see right here, as the latch disconnects, the circuit goes from closed to open. As I go from closed to open, I power off. When the circuit is open, I don't have current running through the wire. When the circuit is closed, meaning the actual mechanical relay there is closed, then I can run current through the wire and I have a complete circuit. Another way to do this is in computer programming. So again, in programming, or if you write software at all, you can detect like when say you have methods or functions within some sort of larger script is going to throw an error. And if it does throw an error, you can tell the bigger script to do something. So these are the instructions that this trap can also contain. The trap can contain instructions about how to pull a low-level alarm and basically start informing either operators or users or anything like that. Start informing other components, even start informing other functions or methods within the software, that basically there was an error with this one certain element of the software of the system. So if anything else downstream is reliant on that, it may also throw an error. And then finally, you can dictate shutdown if that's necessary. So if this is something that is a failsafe, or this is something that's kind of like a e-stop almost, you can tell the system to shut down. So if you detect, a signal strong enough, or if you detect a signal above a certain value, you can say, okay, I need to shut this down. I need to shut down my pump. I need to shut down the valve. I need to stop running the software because there's an error that's just going to propagate and make everything worse. All right, so the last one is Mattia's meta methods. So I thought this was kind of funny. So this figure is actually from the book. This is the out of the box thinking figure from Mattia, because he thought that out of the box needed some sort of visualization. But there's two parts to this. So first we have in the box and we have out of the box. So the in the box meta methods, if you will, are seek consultation, and then two is really go with your intuition. So consultation is really, any outside source that you trust, or any outside source that has a technical background, another engineer, another technician, an operator, somebody else that's not just you and the operator that filed the technical report, that filed the failure report. The second one is intuition. So this is something where you actually need to take a moment and organize all the information you have, take a step back, and then think of how you would take a path towards repairing. So this is something that will take experience, and you'll get better at this intuition aspect with experience. But this is, again, just something that you want to use kind of all the time. Use your intuition all the time, not just when you're stuck. And then outside the box. So think outside the box. So this seems like obvious advice. However, like some of the most obvious pieces of advice are good to share with engineers and technicians and stuff like that, because we get so trapped in our own thinking that we might just spend so much time kind of going down a certain direction, when really that direction we're chasing we're chasing a dragon, we're chasing a rabbit down a rabbit hole. That's not the correct direction, and we've wasted so much time. There's almost this like kind of spent cost fallacy, where we feel like, oh, we've spent so much time in this, like we gotta like see it through, or we gotta finish it off. This is not really the best way to go about it. So breaking the system down into multiple parts, choosing a different starting point, taking a second, taking a breather, go having lunch or go having a walk for a second and kind of thinking about things, that really does help. Talking the problem through with someone, with anyone, whether it be, again, another engineer or someone that's totally disconnected from the problem, just so you can hear yourself think out loud. Sometimes that helps. But, find clever ways that help you think and utilize them. All right, so this is a summary of everything we've talked about today. Again, this is a short lecture, but this is an important one because these are really, like I said, putting tools in our engineering toolbox. And I have that visualized down here with this little tiny 3D printed toolbox. I thought this was super cute and little. But yeah, we're just putting tools in our engineering toolbox. And all of these methods fall within this 7-step structure still. So the methods that we looked at today, we looked at the remove or divide and add and conquers. We looked at the circle the wagon method, fault insertion, trapping, substitution, and then we also looked at Mattia's meta methods, as I like to call them. All right, thank you very much, and we'll talk to you soon.